In this video, we're going to take a look at Hess's law and how we can use Hess's law to figure out the enthalpy change of a reaction. So to get started here, we need to first sort of define what Hess's law is. So we have the total enthalpy change of a reaction is going to depend on only the difference between the enthalpy of the products and the enthalpy of the reactants. It's actually independent of the reaction pathway. And so what's nice about Hess's law then is it's a way for us to calculate enthalpy changes even when the reaction can't be performed directly. So it gives us an indirect route in order to be able to calculate the enthalpy change of a reaction. So before we get into some calculations, we want to talk about what some of these indirect routes are. And we can actually represent those with enthalpy cycles. So I've got 3 enthalpy cycles here. Let's look at the first one here. We have a reaction going from A to B, and we want to figure out the delta H of the reaction. So the direct route is going from A to B. But say we can't actually measure that, but we can measure the route from A to C and then from C to B. Okay, so this is this other pathway here, which is our indirect route. So if we knew what the enthalpy change was, enthalpy change 1 for A to C and the enthalpy change for C to B, then finding the enthalpy change of our reaction is going to be the enthalpy of 1 plus the enthalpy of reaction 2. Now, taking a look at the next one here, A to B again, for our delta H we want to find. And say we know A to C, but then instead of knowing C to B, we know B to C. In order to take this indirect route, we can take the enthalpy change from reaction 1 and subtract it from the enthalpy change of reaction 2. So this is going to give us delta H1 minus delta H2. And it's almost like vector addition, right? So if we're going against the arrow on this indirect route, we're going to take the negative of that value. The last example here, just one other variation. Again, we're trying to find A to B, but maybe we know this time C to A, and we know C to B. So our indirect route, we're going against the direction that we know from A to C, and then we're going with the direction we know for C to B. So this delta H of reaction is going to be minus delta H of 1 plus delta H of 2. So there's a few sort of rules, and this is essentially what Hess's law is telling us how we can use some of these rules with different reactions we know to be able to combine them to then put them back together and find the enthalpy change of a reaction we don't know. So there are several different things. We can have equations, and when I say equations, I mean like A to C, B to C, C to A, so on and so forth. We can multiply them, we can divide them, we can add them, we can also reverse them, which is subtraction, and then we can add them all together to form new equations. We can, if we multiply or divide, then if we multiply or divide the equation, the total enthalpy of the reaction is also going to get multiplied or divided by the same factor. If we reverse an enthalpy, then the sign of the enthalpy change is going to be reversed as well. And then when we add equations together, the enthalpies will get added together as well. So let's take a look at an example and see how this sort of all works together. So in this example here, we're given 2 reactions. We're given this N2 and O2 reacts to give 2NO, and then NO plus a half O2 reacts to give NO2, and they both have enthalpy changes associated with them. And then we're asked to find the enthalpy change for this reaction here. So we can either draw an enthalpy cycle and we can figure it out that way, or we can manipulate the equations. Why don't we start by manipulating the equations? Because I think this is maybe a little bit easier to see. The first thing you kind of want to take a look at is you want to look at your target equation here. Look at reactants and products, and then you're going to try and sort of find the same things in your first couple of equations and see how you can kind of combine things together. So you can see here, like the N2 you want as a reactant, and it's a reactant in the first reaction. The NO2 is a product, and it's a product in the second reaction, but there are two here, and there's only one here. So I think a good strategy to try is we're going to take just reaction 1 by itself and not do anything to it. So I'm just going to rewrite this as N2 plus O2 reacts to give 2NO. And then reaction 2, we need a 2 here in our target equation. So why don't we take reaction 2 and multiply everything by 2. So what that means is we're going to put 2's or multiply every coefficient by 2. So we'd have 2NO, and then 2 times a half is just going to be 1O2, and that's going to give 2NO2. And then if we add those two reactions together, when you're adding reactions together, you add all the reactants together, and then you add all the products together. So I'm just going to bring everything down here and go N2 and O2 plus 2NO plus O2 again reacts to give 2NO and 2NO2. From here, you kind of want to look, is there stuff I can cancel out? Well, we've got 2 NOs on both sides of the equation, so we can cancel those out. We can also collect the 2 O2s together. It's almost like terms in math. It's not really, but it kind of is like that. So we'd end up with N2, 2O2, reacts to give 2NO2, which, if we compare back, is our target equation. So now we sort of know the root. We're taking equation 1, and then we're taking number 2 and multiplying it by 2. We can find the delta H of the reaction by taking the delta H of 1, because we didn't do anything to that reaction, so we do nothing to the delta H. And then we're going to add that 2, because we added these together, 2 times the delta H of reaction 2. Because we took reaction 2 and multiplied it by 2. So if we plug in the numbers, we have plus 181, and then we have plus 2 times negative 56.5, and that gives plus 68 and 1 decimal place, so we need 68.0 kilojoules. So the delta H for the reaction is 68 kilojoules. Now, if we represent this with an enthalpy cycle, we could have done it with an enthalpy cycle instead, but it kind of depends how your brain works and what sort of makes more sense, which way you want to take a look at this. Okay, so to build an enthalpy cycle, we're going to put our target equation here up on the top line, because this is our direct root, and this is what we're trying to find, the delta H of our reaction. So this is our direct root. Now, we know N2 and O2 will react to give 2NO. So this is our delta H of our first reaction. And then we also know we can take 2NO and an O2 to react to give 2NO2. And if we do that, that's 2 times the delta H of number 2. So our indirect root is here. And so you could find the enthalpy change just by kind of drawing one of these cycle diagrams and then going delta H of reaction is number 1 plus 2 times number 2. And that would also give you your plus 68.0 kilojoules. So Hess's law is really neat because you can take lots of different equations, put together their enthalpy changes to find the enthalpy change of a reaction that could be difficult to maybe measure or determine. And so there's a couple of different ways you can manipulate the equations, or you can draw an enthalpy cycle. That's it then for this video. We'll see you in the next one.